Thanks. Hi, everyone. Welcome to the online causal inference seminar. We hope you've had a great Thanksgiving. Today, we are excited to have Yuqi from Columbia University to talk about identifiable deep generative models for rich data types with discrete latent layers. The discussant today will be our Qingyuan Zhao from University of Cambridge. Q&A today will be handled by Emma. So Emma, please explain how it works.
Hi, everyone. Yes, so today there we go. So yes, as always, please submit your questions through the Q&A so that we can answer them and so that everyone else, the participants, can end up seeing them. If you just submit them through chat, only the panelists see your questions. So keep that in mind. Okay, great. I also wanted to say that there will be no official kind of pauses in the talk for questions, so please just submit them as they come up, and then we'll naturally create some pauses for questions to be asked. So just keep asking your questions through the Q&A. And I also want to say before we start, today we're welcoming some of our new panelists who will be joining us soon. Today we have Noah Kiyagami and Sarah Magliacane here, and we'll have some more coming soon. So that's news for maybe some other time, but welcome. Okay, great. Yuqi, please feel free to start the presentation, and yeah.
Thank you. Let me share my screen. Okay, so can you see my slides? Yes. Okay. Yeah. I would like to thank Qingyuan and Ying for inviting me here. It's really my great honor and pleasure to talk about my research in this online causal inference seminar. So I have been working on latent variable models, identifiability, and other aspects of it for a long time. And I've been actually constantly reading into the causal inference literature and getting inspired by some interesting ideas there. But actually, I haven't formally being a researcher of causal inference. So it's really a great opportunity for me to present my work here and to potentially generate some discussions and exploring some new ideas. So today I will be talking about my recent work on identifiable deep generative models for rich data types. And these models consist of discrete latent layers. This work is joined partly with David Johnson from Duke University and partly with my PhD student, Sengheng Li, from Columbia University. So here's a very brief overview of latent variable models. On one hand, these models have been very popular in social and behavioral sciences for a long time. They are used to model constructs that are not directly measurable. For example, personality in psychology, public opinion in political science, or latent skills in education, which is the field that motivates much of my research. On the other hand, we also see that latent variables have emerged as very powerful tools in modern machine learning and deep learning. They can be used to perform dimension reduction, and they are also building blocks for deep neural networks and deep generative models. For example, in variational autoencoders, in deep belief networks, these models all consist of many latent variable models to induce very expressive distributions for complex data objects. So if we try to understand the nature of the latent variable models, we can divide them into basically 4 categories depending on the characteristic of the latent and the observed variable. For example, the factor analysis is a traditional method that uses continuous latent variables to model continuous data, and it has been actually analyzed and used in psychometrics to understand psychological and educational data since a long time ago. And we also know in other cells of this table, we have popular models such as Gaussian mixture, item response theory. And today, I will start with a simple model in the bottom right cell of this table that uses a discrete latent variable to model multivariate discrete data. So the simplest possible model is latent class model proposed by sociologists in 1950s. It is used to understand the different types of people's opinion based on the categorical responses to survey questions. But we know that a univariate latent variable is not expressive in modern applications. And it is desirable in modern applications to consider multivariate latent variables, for example, multiple latent skills in education. And it also is desirable to consider potentially sparse graphical dependence in a graphical model. This can enhance interpretation and encourage dimension reduction. Also, importantly, it is also desirable to consider a deep structure that consists of many layers of latent variables to explain high-dimensional and complex data at the bottom layer. But an important concern in such modeling is that do we understand the identifiability and the property of the latent structures and model parameters? Because we know that identifiability is an important prerequisite for valid statistical estimation and inference. So in this talk, I want to provide a perspective, a statistical perspective from the identifiability consideration. And we will propose a generative model that have many latent layers with discrete latent variables, and they can be used to model rich types of data in the bottom Y layer. So let's start with a simple case with just one latent layer to motivate the key idea. Let's say in this graphical model, the gray nodes denote the observed variables. For example, in educational test, it can be a student responses to P questions. And the latent variable are A1 through AK. They can denote the student's statuses of K latent attributes. And we will consider binary latent variables to start with. Here, each AI just denotes, it can denote the presence or absence of a particular latent skill. And the structure between the latent and the observed layer describes the dependence of the observed items on the latent attributes. Here, the key statistical flexibility we have is that we allow the latent variables A1 through AK to be arbitrarily dependent. And this will be the key to build deep models that are still identifiable at a high level. So as a more concrete example, the TEAMS, or Trends in Mathematics and Science Study, is an international educational assessment, and it has been there for more than 20 years and covering more than 50 countries. So for example, in the TEAMS mathematics assessment for fourth graders, researchers have specified that they are interested in understanding 3 content skills: geometry, number, data, and 3 cognitive skills, applying, knowing, and reasoning of students. So if we want to use the binary latent variable framework to understand this, then the observed variables could be correct or wrong answers of a student to the P questions in the exam. And we want to use the response data to understand the presence or absence of the K latent skills. So we can see that identifiability here is an important thing, because without identifiability, we cannot even make sure the interpretation of each latent variable. So the key structure in this graphical model is actually the edges pointing from the latent to the observed layer. Here's a toy example. Suppose we have 5 questions and 2 latent skills, doing addition and doing multiplication. And you can see the first question here asks for 1 plus 3, so it only measures the skill addition. Therefore, in this graphical model, the first variable y1 only has 1 latent parent. Okay, and the 5th question here measures both latent skill, so it has both parents in this bipartite graph. So this Q matrix, which is a term coined in psychometrics literature, is proposed in 1980s in educational measurement, and it describes this bipartite graph structure of how these observed items depend on the latent skills. Specifically, the QJK will be equal to 1 if and only if latent variable AK is a parent of observed variable YJ. So if we first consider categorical responses for the bottom gray layer, then the model parameters can be summarized as 2 parts. The first part is the parameters describing the distribution of the latent variables. So as I said, we will consider arbitrary dependence between the latent. And simply we can adopt a saturated model in this part. For each possible binary latent pattern alpha, we give it a proportion parameter nu alpha that describes in the population what is the proportion of this particular latent pattern. So there's no other constraint on new alpha, which means we allow any possible dependence among A variables. And to describe the conditional distribution of the Y given the A, if Y is categorical, then we can use the probability theta parameters to describe these conditional probability tables. And note that this graphical matrix, the previous matrix Q, but from now on, I will adopt the notation G, short for graph, to emphasize that this matrix actually summarizes the bipartite graph between the latent and the observed layer. So these theta parameters, these conditional probabilities, actually will depend on this G matrix, because we know that, say here, the first question Y1, it only depends on the first latent skill. Therefore, although we can see this parameter has a subscript alpha, which is a binary vector of k dimension, but actually a lot of them will be equal because the first observed variable does not depend on other latent skills. So a glance at the deep generative structure is provided here. We will consider that in the bottom layer, we still have P observed variables. They are gray, but we have more than one latent layer. This is a directed graphical model with all the edges pointing in the top-down direction and only between two adjacent layers. Specifically, we will use several bipartite matrices, graphical matrices G1, G2, etc., to summarize the structure, bipartite graph structure between consecutive layers. And all the white nodes here are discrete. So the key insight from previous is that since we allow the binary latent layer that is adjacent to the data layer to be arbitrarily dependent on each other, actually we can build a deep model. So before talking about the identifiability in this, at this complicated level, let's just look at a toy example to see what we need to establish identifiability. So let's consider that there are just 3 observed variables and 2 latent layers, while in this shallower latent layer, we have 2 binary latent skills. So now we can actually view the configuration of this latent vector A. It has 4 possible configurations, and it denotes 4 latent classes. So since Y1 here has only one latent parent A1, then we have the following equality of the conditional probabilities. So to understand this, note that if Y1 is just the response to the first question in the exam, since this first question only measures the first skill, so you can imagine a student that only masters the first skill and another student that masters both skills. Actually, they will have the same expected performance on this question because this question does not depend on the second skill. So that is how this bipartite graph, and especially the sparsity of this bipartite graph, induces the equality constraints on this conditional probability.
Hi, Yuqi.
Yeah.
Just a short question from the Q&A. It's just a clarifying question. And that is, how do you decide that A1 and AK are latent? So the person is wondering, I think specifically for this example, because they think that knowing them, they do not think they should be latent. So just a clarifying question.
Oh, so here, because we consider modeling the response data in the bottom layer, that means in such an example, actually, we only get to observe the joint distribution of Y1, Y2, Y3. That is, in this exam, we have 3 questions, and what we observe is each student's responses to these 3 questions. We don't observe their latent skill A1, A2, but we're trying to understand if the latent variable are actually underlying the distribution for Y1, Y2, Y3, then what kind of latent structure can be identifiable? That clear?
Yes, that's clear.
Thanks. Okay, I will continue. So this example actually shows that although the shallowest latent layer consists of many multiple latent variables, but if we flatten them into just a unidimensional latent variable with here 4 latent classes, then we can understand a latent class model with these equality constraints in order to understand this bipartite graph model. So here is the formulation of the constrained latent class model. The white node Z here denotes the latent variable. It is unidimensional, and according to this conditional independence, we have the distribution of the observed P variables. It takes this form. It is the mixture of K product distributions. And this mu and theta are parameters introduced earlier. So here, note that on the left-hand side, we have the joint distribution of only the observed variables. And we marginalize out the latent variable. Okay, so to understand the previous model, we need to consider that these theta parameters, they are actually not freely varying in their parameter space. Instead, they are subject to constraints, the equality constraints. So formally, we introduce a constraint matrix S that has K columns. Note that here, small k means the number of categories that this latent variable Z can take. So it is different from the capital K, which is a number of binary latent variables before. So this S matrix simply summarizes for each question, what level of the latent variables should be constrained to have the same conditional probability. So you can imagine this constraint matrix has a very close connection to this graphical matrix. So for those of the audience that are familiar with tensor decompositions, actually this latent class model formulation is connected to CP decomposition of tensor. In fact, we can write the probability mass function of the observed vector Y as a CP decomposition, where the tensor core and tensor arms are determined by these parameters. Of course, this is a probabilistic tensor, meaning that all the entries are non-negative and they sum to 1. So recovering parameters from this constraint latent class model actually is a problem of unique tensor CP decomposition subject to the same constraints. So it is an algebraic problem. So here, maybe I will first skip some very technical, relatively technical details, and in the Q&A session, I'm very happy to go through these more technical aspects. But here is our definition of identifiability of constraint latent class models and our result of identifiability conditions. So we will say that the constraint latent class model is strictly identifiable if for any valid parameters, theta, s, and nu, the following equality holds, if and only if the two sets of parameters are identical up to a latent class permutation. So note that here, this equality is about the equality of probability mass function of the Y vector under the two sets of parameters, because Y is the only thing that we observe. We don't observe the latent variable. So we can only start with, we can only examine the joint distribution of the observables. Here, we are able to examine the algebraic structure of the constraint latent class models and obtain the following transparent conditions for identifiability. Here, if we suppose the number of latent classes is known and the proportion of each latent class is positive, then if there exists a partition of the P observed variables into 3 disjoint sets, such that each submatrix of the constraint matrix corresponding to each of these sets has mutually distinct column vectors, then the parameters are strictly identifiable. Note that this constraint matrix S actually is a binary matrix, and it simply describes whether or not different latent levels should have the same conditional probabilities. So actually, this condition for identifiability is very transparent, and it merely requires that the constraint matrix S vertically stacks 3 copies, vertically stacks 3 matrices, each of which has distinct column vectors. So now let's understand how this result inspires us to establish identifiability for our generative model with multiple latent variables. Note that previously in the toy example, we have seen that we really examined the bipartite graph in order to get the equality constraint. In fact, there is a one-to-one correspondence between the bipartite graph matrix G and the constraint matrix S. So here in this example, we see the G matrix has the size 3 by 2, and the S matrix will have size 3 by 4, where the 4 columns are indexed by the configurations that this A layer takes. And each entry of this S matrix can be determined by each row of this G matrix. So particularly what we have is that if the G matrix contains an identity matrix, IK, then the constraint matrix S will contain mutually distinct column vectors. So if we combine this observation from the previous theorem on strict identifiability, then we get a very intuitive condition on the G matrix. That is, as long as the G matrix contains 3 copies of identity matrices, it vertically stacks 3 identity matrices as submatrix, then the corresponding bottom 2 layers should be identifiable. Okay, and this is just because we have a one-to-one correspondence between G matrix and S matrix, and we can read off one matrix from the other one. Okay, so actually this is not hard to get if we look at this closely. Okay, so here is the we call it Bayesian pyramid model for modeling multivariate categorical data. The bottom layer are P observed categorical variables, where each variable Yj can potentially take Dj categories. We only require Dj is at least 2, is a positive integer that is at least 2. And here, this is a directed graphical model, and we require the distribution of each variable depends only on its parents. And the parent information is summarized in these bipartite graph matrices, G1, G2. So this G1 matrix has rows corresponding to the P variables in the bottom and columns corresponding to the K1 latent variables in this layer. And similarly, G2 has its rows corresponding this shallowest latent layer and columns corresponding to this second shallowest latent layer. And each entry here is just a binary indicator of the parent-child relationship, whether it is there or not.
Yuqi, sorry to interrupt. There's 2 more questions in the Q&A, so I'm just, is that okay?
Yeah, sure.
Yeah. All right, the first question is, could you have partial identifiability in this context?
Yeah, that's a good question. So I think we have a slightly weaker notion called generic identifiability that I will talk about later. So here, strict identifiability means when the parameters vary everywhere in the parameter space, there will be identifiable. But generic identifiability means that when parameters vary almost everywhere in the parameter space, potentially excluding a Lebesgue measure 0 set, we can have identifiability. Yeah, but for other possible relaxation of the identifiability notion, I think it would also be interesting to consider. Yeah, but sorry.
All right, another question. Could you explain what the parameters are in the definition of identifiability?
Sure. So here, the theta just collects all the conditional probability of Yj given the latent. So here, recall that in this latent class model, the theta JCH just means conditioning on the latent variable is equal to H. Then what is the probability that Yj takes the category of Cj? Okay, so this is conditional probability of Y given Z. And nu H are just the proportion parameters for the latent variable Z. So this is denoted as theta, this is denoted as nu, and S just collects these constraint matrix entries. So in this identifiability definition, we require our conditions are only imposed on this discrete structure S, but our conclusions actually hold for all these components in the model, the theta, the nu, and the S.
Okay, thank you.
Thanks. Okay, so following the convention in probabilistic graphical model, we can write out the conditional distribution of each layer given its parent layer as the factorization in this form, because we have conditional independence. And in the end, if we multiply all these conditional distributions, we get the joint of all the variables. But since only the bottom layer is observed, we need to marginalize all the latent layers. So you can imagine the resulting distribution for the observed P random variables at the bottom could be quite rich and flexible. And if we can have identifiability for such an expressive distribution family, then we can use it to model complicated data. So this result summarizes our identifiability conditions for Bayesian pyramid. So in fact, we have very transparent conditions that only depend on the structures of these bipartite graphical matrices, G1 through GD. So suppose there are D layers, and this GM, it just describes the parent-child relationship between the consecutive layers. And each of it is a binary matrix. We require that it vertically stacks 3 identity submatrices, and there could be a remaining submatrix that takes an arbitrary form. As long as this condition is satisfied, then the following properties are identifiable. The probability distribution of the Z and the conditional distribution of the other variable given their parents, and also the bipartite graph structure between any 2 consecutive layers. So they are identifiable subject to up to the latent variable permutation within each layer, because that is the inevitable and trivial ambiguity there. So here we assume that the number of latent variables in each layer are known. Okay. So this condition actually can be translated into the graphical language and has an interesting implication on how this deep generative graph should grow. Because we require that here GM contains at least 3 identity, it really means that each latent variable, regardless of which layer it is in, it should have 3 exclusive children. Exclusive means that this variable only has 1 parent, then it is an exclusive child of this latent variable. Note that we do not constrain the graph here to be a tree, because we allow a structure like this. So here Y2 has 2 parents. It is allowed, and this structure can be absorbed into the GM star part. Okay, as long as there exist 3 exclusive children, then we can have identifiability. And note that this condition also implies a natural constraint on the number of latent variables in each layer, because it naturally constrains that K1 can be at most P over 3, K2 can be at most K1 over 3. So we have smaller and smaller latent layers when we go deeper. Actually, this is consistent with some empirical wisdom that when we build representation, when we try to extract latent representations under complex data, then actually we should try to extract more and more abstract and general features from data when we move away from the data layer. And in psychology, actually, it's also interesting to uncover a hierarchy of latent concepts. For example, the bottom layer are just a large number of question responses in the exam. And the shallowest latent layer could be very fine-grained skills. And the deeper latent layers could be more general skills, such as number geometry. And even deeper, we can have even more general concepts, such as math, physics, etc. So it is consistent with some conventional or empirical observation that we want the latent representations to be having a fewer number when we go deeper. And also here, the sparsity condition between latent layers can help us pinpoint the meaning of each latent variable, because we can try to understand the interpretation of each latent variable by looking at its children variables and the connection strength in each edge. Here are some discussions between on the connections between our study and some existing work. So in psychometrics, there's a family of so-called cognitive diagnostic models proposed for diagnosing the absence or presence of fine-grained latent skills. They are usually confirmatory in nature with domain knowledge as input. That means all these, so actually they have only one Q matrix that describes how the questions depend on the skills, and that is often given by educational experts who design the exam. But here we assume that this matrix itself is unknown, and we try to identify it from data. Also, deep structures have not been considered there. In machine learning, actually there are related models that have discrete latent variables, including deep belief networks, deep Boltzmann machines, and vector quantized variational autoencoders. They are very popular and useful in various prediction tasks, but the identifiability issue is typically ignored. So in both these fields, modeling arbitrarily flexible responses with deep layers have not been formally defined, and whether these deep models can be identifiable is unknown previously. So thus far, actually, I have only talked about categorical responses for the Y layer, but here by arbitrary flexible responses, actually, I mean, we can extend our identifiability result to the cases where the Y layer actually takes much more flexible types of distributions. So in this case, we extend our model where each Yj has a sample space curly Yj, and we require it to be a complete separable metric space. It has its sigma algebra and measure. So for example, if Yj is the collection of all the non-negative integers, then we can use it to model count responses. And if Yj is the entire real line, then we can use it to model continuous responses. What we require, as before, is that first, the latent variables are discrete and they can be arbitrarily connected to each other. And second, the graphical constraint, the conditional independence constraint encoded in the G matrices, they are respected. So we have this conditional distribution that only depends on the parent variables of each Yj, but not all the variables. So here you can see when Yj, curly Yj takes different spaces, then we can use it to model different types of distributions. For example, exponential family distribution can be used. Here we allow flexible link functions and also flexible parent-child interactions. This means in order to specify the conditional distribution of each variable given its parents, we actually do not constrain it must take a certain parametric form. And the key and crucial assumption there is that the graphical conditional independence is respected. So possible parent-child interactions include the main effect, basically means the linear combinations of the parent latent variables will enter the conditional distribution. Actually, many examples fall in this category. The restricted Boltzmann machines, noisy or Bayesian networks can be reformulated in this form. But we can also adopt a more parsimonious model. For example, constraining that the conditional probability of each variable given its parents to only take two possible levels due to some Boolean interaction. Or we can consider more complicated models that include not only these main effects, but also potential interaction effects of these parent variables. But as long as the G matrices still play a role and conditional independence is respected, then our identifiability result still holds. So we still have that when the graph takes the form in the previous slide, then we can identify the parameters and the graph structures themselves. So here we summarize the result for identifiability in this general response case. Yj belongs to general sample space curly Yj, and we also in this result, compared to the previous slide, you may notice that we relax the requirement of the number of exclusive children from 3 to 2 due to some blessing of dependence phenomenon. So without going into details, I just would like to comment that actually this condition looks very similar to the categorical response case, although here we consider much more general sample spaces. And the high-level intuition is that we actually do a binning of the sample space of a general observed variable and define surrogate categorical variables. Okay, so that's the high-level idea. But before that, I also want to comment that corresponding, partly related to the previous question on partial identifiability, here we establish generic identifiability for a specific subfamily of model. That is the main effect-based model. The main effect model has this generalized linear model form, where you can think of these latent parents serving as covariates or predictors in a GLM, okay, but they are latent now. So as long as we have this main effect structure, then we no longer require the G matrix to contain those two identity. Actually, we relax the condition to that. It only needs to contain two K by K submatrices where the diagonals are equal to 1, but any of the off-diagonal entry is free to be either 1 or 0. So this largely relaxes the previous requirement and can allow actually a dense bipartite graph between layers for this main effect-based model. Okay. So also this condition can be translated to graphical language in that we can find two matches from the observed, from the latent variable to the observed variable, but they are not perfect matches compared to the previous result in graph theory terminology. Okay, so here a little bit more detail of how we go from categorical to non-parametric distribution. So when we consider that the Yj actually has a non-parametric probability measure, but we still have discrete latent variables and have conditional independence, then we can actually factorize this distribution, joint distribution of the observed variables still in this way. This is a finite mixture of non-parametric measure products. And we will construct a binning of each variable Yj using some cut points. So if the sample space Yj is a real line, then it is partitioned into several consecutive intervals. Then we will define a surrogate categorical response variable by just collecting the binary indicators of whether the original Yj belongs to each of these intervals. Then we can use the bipartite graph condition to prove identifiability about the conditional distribution of the surrogate given the latent. But since these cut points are kind of arbitrary, as long as certain rank conditions are satisfied, so we can go back to establish the identifiability of this conditional distribution for the non-parametric probability measure. So that's how we actually are able to translate our identifiability conditions in the categorical case and still have similar conditions in the general response case. So I think I also like to give a few remarks on the identifiability results and the proof. So since I mentioned that the structure in our model with these discrete latent variables actually has a tensor CP decomposition form. And there's a classical algebraic result established by Kruskal in 1970s. It says that a three-way tensor decomposition actually can be unique under quite mild conditions on the rank. So this result offers a way to prove uniqueness of tensor decompositions by checking certain global rank conditions. And in the first result that I talked about today, with the three identity matrices in a G, actually we used this result in the classical Kruskal's paper. But we also propose a more fine-grained algebraic technique to study identifiability of individual parameters rather than checking global rank conditions. So then this technique allows us to actually establish identifiability under complex graphical constraints and sometimes obtain weaker conditions compared to Kruskal theorem. But I would say the high-level idea actually is the spirit is similar to Kruskal theorem by looking at these tensor decompositions and how graphical model conditional independence induce a lot of constraints there. So using this technique, we can deal with non-Gaussianity, non-linearity, and also graphs well beyond trees by examining polynomial equations given by higher order tensors. Note that, say we have p observed variables in the bottom layer, and the joint distribution, even if each of the observed variable is just binary, but what we have is really a p-way contingency table or a p-way tensor. So in order to study identifiability, we need to understand these polynomial equations given by these higher order tensors, rather than the covariance matrices, which arises when in a lot of study in linear structural equation models with Gaussian latent variables and observed variables. Okay, and the arbitrary dependence among the latent variable allows us to go deep, because here the intuition also is, I think, is simple and intuitive, because the way we can go deeper is by first focusing on the bottom two layer and marginalize out all the deeper latent layer. Then you can imagine the distribution of this shallowest latent layer could be quite complicated. But since our identifiability condition for the bottom two layer is established for arbitrary dependence among the latent, so we can actually only require conditions on the G1 matrix to have identifiability. And the identifiable quantities in this stage includes the joint distribution of this shallowest latent layer. And once this joint distribution of the shallowest latent layer is identified, actually this brings us back to the case that as if this layer is observed. So then we can actually proceed in a layer-wise manner. And this is actually not possible if we have, say, continuous latent variables, or if we are not able to deal with arbitrary dependence. Okay. Yeah, so the last point here I want to make is we also have the extension from categorical to very flexible types of responses. So that provides opportunities to model data that are also can take mixed type. For example, some of the observed variables are continuous and some of them are discrete. That's also possible. But the key is that we have discrete latent variables. And they can be either, they are not necessarily need to be binary. I want to very briefly go through the estimation. So actually, one thing we have is once the model is identifiable, then the maximum likelihood estimator will be consistent. And the Bayesian estimator will also have posterior consistency when the priors have full support around the truth. So that's pretty natural corollaries. Okay, so as an illustration, we focus on the two latent layer model with one binary latent layer and one discrete deeper latent variable. So we have a latent class model for A layer given Z, and we have a generalized linear model for Y given A. So in this case, since we have the main effects in the GLM, we can apply generic identifiability conditions. Actually, for different types of responses, we adopted a different estimation method. We have tried different estimation methods. We have tried Bayesian shrinkage estimation for the categorical response case, where we impose non-parametric Bayesian priors to estimate the latent structure and use data augmentation to develop a Gibbs sampler. And for frequentist shrinkage estimation for general response, we have used lasso and group lasso penalties in order to estimate the bipartite graph structure. Because actually in the previous main effect model, you can see the graph really plays a role of specifying what coefficients should be 0 or not. Okay, so we can use some penalty in order to estimate the graph structure between layers. And we can use EM algorithm for exponential family responses at the bottom layer. The simulation results also corroborate the identifiability conclusion. So here I show the mean estimation error of the graphical matrix between the A layer and the bottom Y layer. You can see this is actually a relatively challenging scenario. We don't have a large sample size, but the number of cells in the contingency table is huge because we have 20 categorical variables, each of which has 4 categories. but for relatively not so large sample size, the estimation of the G matrix is quite accurate here. And if we look at the estimation root mean squared error of continuous parameters in the model, then this plot of RMSE versus 1 over square root of the sample size shows that we have the usual statistical convergence rate. So it is an empirical validation of good statistical performance. I also want to talk about...
Hi, Yuqi. Sorry to interrupt, but we are nearly running out of time. Can you quickly wrap up in like 2 or 3 minutes?
Sure, yeah. So, so I think I will only talk about maybe one real data example. So we applied the method to nucleotide sequence data and observed that the estimated latent representations in totally unsupervised manner are actually very predictive of the held out information. So that means in a downstream classification where we used latent representations to predict the sequence type of each nucleotide sequence, actually we achieve an accuracy that matches fine-tuned CNN. So that is in terms of prediction. And in terms of illustrating the general response, we applied the method to an educational assessment dataset, which is an application that has motivated my research for years. And in this dataset, we consider each student's response time to each of the questions. And we are able to use our model to uncover the, here is a correlation plot among the 7 latent skills in this exam. And we can see this identifiable model, it gives rise to very interpretable structure in this correlation because the 4 content skills, number, algebra, geometry, data, they are highly correlated. The 3 cognitive skills, knowing, applying, reasoning, they're highly correlated, and they're relatively smaller correlation across 1 content and 1 cognitive skill. Okay. So in the end, I want to give a very brief brainstorming about the connections between this study to causal inference. So I think it may be interesting to pursue causal discovery among the latent variables, because since we allow the latent variables to be arbitrarily dependent and are able to identify their joint distribution, then combined with some ideas in causal discovery among discrete variables, then maybe we can try to understand the causal relationship beyond the correlation here among latent variables. And also, since we have a deep generative model here, and we can identify the structure in this deep generative model, I feel this work is also related to causal representation learning, where people try to use the lower dimensional latent variables and disentangle them. Also, it may be interesting to consider causal inference under unobserved latent confounding, where the latent variables not only serve as substantively meaningful constructs like latent skills or biological sequence types, but they also serve as confounders, and how to use these identifiability result in that setting or generalized result in that setting, I think it would also be interesting. So thank you very much for your attention. Thank you.
Thanks, Yuqi. Can I just ask a short question from the Q&A and before we move on to the discussion? So a person has asked, could this be an infinite mixture? Like, could there be an infinite mixture, I guess, of these latent?
So in the results that I presented, actually, we have assumed the number of latent variables are known. So they are a finite mixture. Yeah, but but I think it is, although technically non-trivial, but it would be interesting to consider how to identify the number of latent variables and maybe start with an overfitted mixture model. Because in the estimation procedure, we have tried Bayesian non-parametric prior with an infinite mixture to start with, and we are still able to estimate the number of latent variables. I mean, that's empirical observation.
Thank you. Okay, let's move on to the discussion. Yuqi, if you can stop sharing, that would be
actually, it's fine if you keep sharing. I did not prepare any slides. So what I would do is, well, first of all, I'd like to thank Yuqi to give this really nice talk about her work. So what I will do is I'll just give some high-level comments on Yuqi's talk, and then I'll try to ask specific questions on some of the slides that I found a bit confusing when I read through the slides. So my first comment is on the on related literatures on identifiability and causal inference. As far as I know, there are two related literatures. One is on linear structural equation models, and there's a lot of work by Matthias Durton and his collaborators. I think I see Yuqi has cited them here. And arguably the technique, the mathematical techniques are a bit different. I think there's a lot of more kind of algebraic geometry in that kind of linear models. But I think it looks like Yuqi's work was based on Kruskal's theorem and sort of tensor decomposition of probability distributions. But when I looked at the proofs, I did see some kind of algebraic varieties. So maybe there's a connection that I'm not aware of. There was another literature on sort of non-parametric identifiability of causal effects from causal graphical models with latent variables. So examples include the Duke calculus, the ID algorithm, and also these more recent, I guess this is more closer to generic identifiability using proximal sort of proxies for confounders. I'm not an expert in that area either, but I did notice there's some similarity and connections to the results presented here. My second high-level comment is on, I guess, Yuqi's last slide about connections to causal inference. So for most of the talk, there's no mentioning of causality, but you can easily imagine these Bayesian pyramids could have applications in causal inference. I think particularly this is the case in social sciences, where in many problems, cause and effects are often best constructed as abstract latent variables instead of something we can measure. And the TIMS dataset that Yuqi gave us is an example of that kind, where we want to assess students' aptitude in geometry or reasoning. Those are quite abstract concepts. So Yuqi gives an example where she could find sort of correlations between those latent kind of aptitudes, but it can be imagined that you can modify the model, perhaps either using more like a structured learning kind of approach, or you can, in the more conventional approaches, to specify some kind of causal structure between the latent variables, and you can do some kind of causal inference there. My third high-level comment is that looks like I just need to turn on my light. Excuse me for a minute. My third comment is that I think this is really a very exciting. This opens up a really exciting kind of direction for psychometrics and perhaps a lot of other social science areas. I think a lot of in those areas, a lot of people use linear structural equation models as their main research tools, and the methodology and computational software for those were largely developed, as far as I know, in the 1970s and 80s, and they're often fraught with statistical and numerical issues. I think what would be really interesting is to understand how these modern tools, computational tools for deep neural networks, and also the modern theory for causal graphical models could be used to significantly upgrade our toolbox for these latent variable models. Related to what Yuqi mentioned on the last slide, I think there's also this emerging area, especially in machine learning, called causal representation learning, where people are interested in giving causal explanations to high-level features learned by neural networks. I don't think people have gone particularly that far in that direction, but it was really interesting to see some of the examples emerging from sort of features you can learn from images. And it would be really interesting to see if the identifiability presented here and also developed in the causal inference community can be useful to solve conceptual and theoretical issues in that area. For example, one, I guess, simple, silly, probably silly question is that given what Yuqi has shown us, is it actually a good idea when we construct the architecture of a neural network? Should we actually always require every neuron to have at least 3 exclusive children in the network? Because that would make the neural network identifiable, but I don't know what the machine learners would say. Okay, I have 3 more minutes, so maybe I'll just ask some quick questions on some of the slides. Yuqi, can you share your slide again and turn to number 17, where you described this transformation from G to S?
Yeah. Okay. It has some.
Yeah, it's number 17. Yes.
Oh, 17.
So
yeah,
I guess I'm generally a bit fuzzy about what this S matrix, this constraint matrix S means.
Okay.
So I can see there's a map from G to S, but first of all, why is this constraint? Why is it enough to use just a binary constraint matrix?
Yeah. So actually, this is an intermediate tool that we use to translate the identifiability in this constraint latent class model to this bipartite graphical model. So actually, it is not the only way to prove identifiability in this model, but I will try to explain a bit the relationship. So here, the S matrix, the entry is determined by 1 minus the binary indicator of whether the corresponding latent pattern in this particular column is element-wisely greater than or equal to the corresponding row vector there. So basically, S is encoding the information that whether this latent pattern is considered as not capable. So if we think of this from still an ability and education context, then as each entry is a binary indicator of whether the corresponding ability pattern is not capable of the this particular question with this skill requirement profile. So then if it is not capable, then actually they will be constrained to have the same conditional response probability for this particular question. Yeah, so it actually does not include all the information in this bipartite graph, but actually extracting this much information already allows us to translate the condition on the S matrix to the G matrix and obtain the requirement that in this bipartite graph, each latent variable needs to have at least 3 exclusive children. I don't know if that is.
Okay, that's helpful. Maybe I'll just ask one last question. Can you go to slide 21, where you presented your theorem of the identifiability of Bayesian pyramids? So I guess here you basically said that for strict identifiability, one sufficient condition is that each latent variable needs to have 3 exclusive children. So this reminds me of these kind of 3 indicator rules in latent vector models where everything is continuous. Can you comment on the if there's any connection to those results?
Yeah, that's a great question. So also related to your high-level comment earlier, that the consideration of identifiability for linear structural equation models with continuous variables actually is connected to our study in these models with discrete and potentially deep latent structures. And the difference is that in those cases, when studying identifiability, first, I think the similarity is that we will just focus on the polynomial equations given by the observed distribution and examine whether under what conditions these polynomial equations have unique roots, because unique roots means that we can identify things. So, but in continuous latent variable case, all the especially if we have Gaussian latent and observed variables, then all the information about the joint distribution of random variables is encoded in a covariance matrix, which is just a matrix structure. And the polynomial equations are about the entries in that matrix. And traditionally, the 2-indicator rule, the 3-indicator rule developed by factor in the factor analysis literature examines these polynomial equations, which involves the entries in the covariances and variances, and discover that structure. But in our study, because we have discrete observed variables to start with, then the joint distribution of observed variables, as long as we have more than 2 observed variables, then we have a tensor. And we cannot use covariance to summarize their joint distribution, because the joint distribution of 3 binary random variables, even if we know their covariance and their mean, right, we don't know the joint. So therefore, the polynomial equations actually will take different forms. But I think it's a very interesting, in terms of technique, how we get the 2-indicator rule here and in traditional factor analysis is quite different. But it's very interesting that in this like algebraic statistical consideration, in both cases, these 2-indicator and 3-indicator rules are sufficient for identifiability. So I think I still could not give a like very intuitive explanation of why they are exactly the same kind of condition. But yeah, I would say they both belong to algebraic statistics investigation of polynomials, but actually they are arising from very different structures like matrices and tensors.
Okay, thank you very much.
Great. Thank you for the great talk, Yuqi, and thank you, Qingyuan, for the inspiring discussion. I think it's a good point to wrap up. We still have a few questions in the Q&A, but due to the time limit, we'll just stop here. So we will forward the questions to Yuqi, and if you're interested, feel free to follow up by emails also. So I'll share the final slide. So next week, we'll have Erica Moody from McGill University to talk about flexible modeling of adaptive treatment strategies for sensor outcomes. We hope to see you next week. And stop sharing.